All right, here we go. Second kinetics lecture. As you can see, I'm wearing the same clothes, so it's not like it's the second day, it's just a couple minutes later. All right, here we go. All right, so I'm going to pick up where we left off. And so where we left off was discussing all of these different types of rates. There was the absolute rate, there was the relative rate, there is the instantaneous rate, the average rate, and the initial rate. And all of these will be somewhat different, okay? And also, depending on what time you are at in the reaction, they'll be different. So what we need is a rate constant, okay? And what we also need is some type of an equation that will give us this rate constant. And so that's what we have right here. We have the rate constant, K, and I know that there's K's for equilibrium, and there's K's for kinetics. So in kinetics, the rate constant is a lowercase k, not a big uppercase K for equilibrium. Okay, so we use lowercase k for kinetics. We use uppercase K for equilibrium. And so that rate constant, it's a proportionality constant that relates the rate of a reaction to the concentration. Okay, and the idea with the rate constant, it is constant throughout the entire time of a reaction. There's the rate law, and that's an equation that defines the experimentally determined relationship between reactant concentrations and the rate of a reaction. Sometimes we also call the rate law the rate expression. Okay. And then finally, in the rate expression are reaction orders. And the reaction order is an experimentally determined number that defines the mathematical dependence of the reaction rate on the concentration of reaction. So these reaction orders are typically whole number integers. And there's only going to be a few that we do in this class. We're going to do zero order, first order, and second order. And that's it. 0, 1, and 2. Okay. So if all of these definitions are a bit confusing, that's okay. As you know, I like learning through example instead of learning through definition. So here are the definitions. So let's move on and talk about this in terms of examples, or just putting out the equation. Okay. So if we have the generic reaction, let's say A plus B goes to C, then we first start by writing the reaction as rate equals, and we note that that rate could be negative delta A over delta T. It could be negative delta B over delta T, or it could be positive delta C over delta T. So by saying rate, I can really make this relative to any of the reactants or products. But now, as a convention, okay, and it doesn't mean that it's a requirement, but as a convention, we always write reaction orders in terms of reactants. It's all about the reactants. We could still, I shouldn't have X'd this out, excuse me. Let me keep that there, okay. It's all about the reactants. Okay. So now here's how the following rate expression goes. We first say rate equals K. So that's K, a rate constant, okay? And it's going to be, now this is where it's all about the reactants. On the right-hand side of the equation, we're going to write the concentration of both reactants multiplied by each other. So notice I don't have any C in here. It's just A times B. It's all about the reactants. And then we're going to raise those to some power that we call the reaction order. And so this creates our rate law, this equation, or sometimes the rate expression. Okay? And we also note, because we have this way of doing all of these relative rates, as you can see on the slide here, we could say this rate expression is equal to the rate of A, it's equal to the rate of B, or it's equal to the rate of C, because the way all of these are written, they're written as relative rates, meaning they're all equal. But once again, we always take any reaction. We only deal with the reactants, okay? And it's K times reactant concentration raised to its reaction order times the other reactant concentration raised to its order. If there was only one reactant, we'd only have one reactant on this side. Okay, now for the reaction orders, we're going to have to spend a lot of time talking about this because as it turns out, the reaction orders can only be determined experimentally or through a theoretical analysis of the mechanism. So this is not like kinetics where if we knew, like for example, if I had a 2 in front of there and I put a 2 right there, that's not how this goes, okay? So if I were to put stoichiometric coefficients here into my generic reaction, okay, M does not necessarily equal little a, and N does not necessarily equal little b, though they can, I should say, not necessarily, assuming I can spell necessarily. Okay, so they could be equal to the stoichiometric coefficients, but they don't have to be. And so we're going to have to spend a lot of time figuring out how we determine these reaction orders. But once again, they're going to be whole number values. They're typically going to be either 0, 1, or 2. Those are the only cases we're going to deal with. So concentration raised to the 0 power, concentration raised to the first power, or concentration raised to the second power. Okay, so let's move on and go to a specific example. All right, so here is the example reaction. 2 NO2s react to form 2 NO plus O2. And so I could write this, I'm just going to write generically and say rate equals, and that's going to be K times NO2 raised to some power, and we don't know what that power is yet. And it's tempting to want to put a 2 right there, but don't do it. This is not equilibrium. This is kinetics. All right? And so, of course, I just said rate equals K times NO2. And you notice on the slide, it was written as negative NO2 over T equals KNO2. This would be doing it like in terms of the absolute rate of NO2. And then, of course, if I keep that there, that should be negative delta NO2 over delta T equals K NO2 raised to some reaction order. So now the fact that I've kept that without the 2 right there, that means it's going to be equal to positive delta NO delta T equals K NO2, because I can see that my NO2 and my NO both have a coefficient of 2, so they're the same proportionality. But now my O2 just has that coefficient of 1. So if I wanted to relate that to the O2 coefficient, I'm going to do the opposite of what we did before and say plus 2 times delta O2 over delta T equals K NO2 raised to the power N. All the same, no matter what rate you put on the left, they're all just a rate. So that's why we just say rate equals K times NO2 raised to the N. The real magic of this equation here is the right-hand side. This is what's important. Okay. So how do we figure out what N is? Well, again, there's 2 ways we can do it. We can do it experimentally. So someone would have to run this reaction and measure concentration versus time. Or if we could analyze the mechanism theoretically, and the mechanism is all of the different steps going on in the reaction, then we could do it. And we're going to talk about both of these methods. Analyzing the reaction mechanism theoretically is quite hard, and it's something you will spend like your lifetime as a career chemist doing, if that's what you end up doing with your science degree. So we're only going to crack the beginning of how we analyze a mechanism. We're going to spend a lot more time in understanding how we analyze the data to get that coefficient of N. Okay, so I'm going to switch the slide here. And so now I'm going to give you a different reaction example. And so this reaction is 2 into O5 makes 4 NO2 and O2. Okay? And then so if we first were trying to decide what the reaction expression, what the rate law is going to be, we could say rate equals K, and then only times the reactant times N2O5 raised to some power n, and we've got to use the data to figure out the power n. So now here on this graph, what someone has done is they figured out how to do measure the concentration of N2O5 over time, and this is no easy task. And this is something that our upper division chemistry students do in PChem lab, and it's actually quite hard to measure concentration versus time accurately. So typically you use spectroscopy to do it, and if you remember some of your labs where you used the little SpectraViz I think that was for the dissociation constant lab and for the I'm drawing a blank here, but anyways, where you did the colorimetric analysis, that's typically how these concentrations versus time would be given, by doing the reaction inside of some spectrometer where you can measure in situ the concentration. It's not easy. It's what I do in my own research, and I can tell you it's not easy. In any event, someone did this experiment, they ran the reaction, and then what we have going on here is the following. If I look at this data here, I'm going to recopy this table so you can see what I've got going on. And at one data point, they knew that it was 0.9 molar, so perhaps that's that data point there. And if we looked at the instantaneous rate, and that's molarity per second, right? So if you notice here, this point right here, we've got, that would be the slope of the line. That would be the instantaneous rate. And someone found that it was, so this is 0.9 molar, and someone found this was 5.4 times 10 to the minus 4 molarity per second at that data point. And then now at another data point here, where the concentration is 0.45, of course the instantaneous rate is different, and they found that it was 2.7 times 10 to the minus 4, okay? And of course we could keep going, right? We could actually list every single one of these data points, concentration and the rate, if we wanted to, but we only need 2 data points technically. We only need 2 data points for one reactant. If we had 2 reactants, we would need 3 data points. If we had 3 reactants, we would need 4 data points, and I'll show you how that works momentarily. Okay, so now, as you notice here, what this says, when concentration is halved, the rate is halved. So what I mean by that is, when I go from this data point to this data point, the rate went down by 1/2, or I could look at it from saying, you know, if I go from this data point to this data point, the concentration goes up by 2. So either way, like if I go from here to here, concentration went up by 2. If I go from here down to here, concentration went down by 1/2. So now if I do the same thing, suppose I go from this rate to this rate. Well, 2.7 times 10 minus 4 is exactly half of 5.4 times 10 minus 4, okay? And so what that means is when concentration went up by 2 and the rate went up by 2, then we can do the following algebra. We could say, well, there's a couple different ways we could do it. For one, if we just inspect this equation here visually, if rate goes up by 2 and concentration goes up by 2, then that means N has to equal 1, okay? So, and I'll prove that to you. So for example, suppose we have my rate of 2.7 times 10 minus 4, and that equals K times, and then if I'm using this rate, I have to use this concentration, 0.45 molar. And suppose here now we're just going to guess, or if we looked at this and we said, oh, if that goes up by 2, that goes up by 2, that means that that N has to be equal to 1. Here's how I'll prove that to you, okay? So if now what I can do here is solve for K, right? I could say K equals 2.7 times 10 minus 4 divided by 0.45. And when I do that math here, let's see, I got 2.7 e to the minus 4 divided by 0.45, and I get that my k equals 6 times 10 to the negative 4. Okay, now what if I try it for the other data point? So if I say now 5.4 times 10 to the negative 4 equals k times 0.90, and I do the same thing. I solve for k by saying 5.4 times 10 minus 4 divided by 0.9, and that's 0.9 raised to the first power, okay? So 5.4 e to the minus 9 divided by 0.9, and I get 6 times 10 to the negative 4. Let me just double check that because I think I hit the wrong button. Yes, I get 6 times 10 to the negative 4. And so what that means is at this data point, so if I look at my k value, here my k was 6 times 10 to the negative 4, and here my k was 6 times 10 to the negative 4. And of course that unit is going to be, we're going to talk about k units soon, but that was a molarity per second divided by molarity. So that k has units of 1 over seconds. And so now if I were to do this for every single data point, right? If I got a rate and a concentration for every single data point along this line, and recognizing that this concentration, this n reaction order, has to be to the first power, and that's entirely based on this data, this data right here, then I would get the same k for each and every one of those data points, and that's exactly what makes this a rate constant. Okay? So it's a bit of a challenge figuring out what the reaction order is, and I'm going to give you a systematic equation on how we do it soon. But the important thing to recognize is the reaction order. This thing gives you the dependence of concentration on time. Okay, it tells you how concentration will vary with time, or it tells you how the rate and the concentration are related to each other. So in this reaction, when the concentration doubles and the rate doubles, it has to be a first order. I'll give you another example here, okay? And I'll give you this example orally, but then we'll also work through this example on another slide. Suppose when the concentration doubled, the rate went up by a factor of 4, okay? So if concentration goes up by 2 and rate goes up by 4, that means the reaction order would have to be 2, okay? And I'll show you an example of that soon, all right? So here's an example of this, what these reaction orders are doing, okay? So suppose I have this reaction now, NO plus O3. And I'm also going to already tell you that both are first order. Okay, so when I write this reaction, rate equals K times NO times O3, and I'm going to write a 1 here, and I'm going to write a 1 here, even though we don't normally need to put that it's raised to the first power, right? I'm going to write that in there and say that in this specific reaction of NO reacting with O3 to make NO2 and O2, someone already did the work for us. Someone already figured out that it's first order in NO and first order in O3. Okay? Well, what that means is this reaction is second order overall. Okay? So if this is first order in NO and first order in O3, that means it's second order overall because 1 plus 1 is 2. So here's a demonstration of that. Suppose we have one NO molecule and it reacts with one O3 molecule, just as it's showing here. So if I have one of each and they collide. 1 times 1 equals 1. That's one collision. And we have to consider now, right, in order for things to react, the amount of time it actually takes for them to react is very much related to how much time it takes to them to find each other and collide. So now when there's only one NO and one O3, there's only one possible collision. But now suppose that I have 2 NOs and still one O3. Well, that would be 2 possible collisions because the O3 can either collide with the NO, with one NO, or the other NO. But now, here's where the magic happens. Suppose I have 2 of each. I have 2 NOs and 2 O3s. That creates 4 possible pairwise reactions. And that's exactly where we're seeing this second order situation. If I have 2 of each, I get 4 collisions. Look, if I have 3 of each, I would get 9 collisions. If I had 4 of each, I'd get 16 collisions. If I had 5 of each, I would get 25 collisions. That's exactly what it means to have this second order reaction. And so in this second order reaction, that means the reaction rate is going to increase with the square of the concentration because of all of these possible collisions. So increasing concentration increases collisions, leading to the formation of more products. Okay. And as you might imagine, if we had a third order reaction, okay, having 2 and 2 of each would lead to a factor of 8 because 2 cubed is 8. Having 3 and 3 of each would lead to a factor of 27 because 3 cubed is 27. So that's what this reaction order is getting us to. All right? So what gives a reaction its order? Determining a reaction order experimentally requires examining the reaction data. We have to see how the rate depends on time and concentration because with kinetics, it's unlike any other branch in chemistry. We just don't really have a good way of predicting what's going to happen unless, point number 2 here, determining a reaction order theoretically requires a detailed examination of its mechanism. That's really hard, and that requires a lot of insight in chemistry. So we're going to predominantly focus on this first one, but later on in the chapter, maybe in my 3rd or 4th lecture here, we'll talk about this very briefly as just an introduction. Okay. So so now what I'm going to do, we're going to look at how we determine a reaction order given a set of data, and we call that the method of initial rates. So I talked in my first slide about how we have all these different types of rates: absolute rate, relative rate, average rate, instantaneous rate, initial rate. Initial rate is preferred. And this is why, okay? Because it allows us to determine a reaction order. So I am going to describe what I am doing here instead of just pausing the video and allow you to work on this on your own, because this is something that's kind of new. I'm going to work through this. And I think that I'm going to recopy the data here just to make life... no, I don't think I'm going to recopy the data. I'll just go ahead and work through this, and I'll show you the systematic way that I choose to work through this. Okay? So here we have the reaction of ammonia and NH4 plus ammonia and nitrite to make H2O and nitrogen gas. Okay? When we first want to start guessing what our rate is, we're going to guess by saying just rate equals rate constant K times my ammonia concentration raised to some power. It really doesn't matter what letter you use. Okay? It could be X, Y, N, M, P, Q. It's just some placeholder. And NO2 minus raised to some power n. And remember, we only do this with reactants. We only write the rate law with reactants. Okay. And so now, because in this case here, this is going to be a little bit more challenging than that very first example I did, I have 2 reactants to work out. And As I said earlier, if I have only one reactant, I need a minimum of 2 experiments. If I have 2 reactants, I need a minimum of 3 experiments. And that's what I have right here. I have experiment 1, 2, and 3. And at experiment 1, 2, and 3, I have so that I right there, that stands for the initial concentration. And correspondingly with that, I got the initial rate. Okay? So I'm going to set up a ratio of equations. I'm going to divide one equation, and I'm going to pick number 2, and I'm going to divide that whole equation by number 1. And the reason I'm going to do that is because I want to attempt to eliminate variables. So I want to eliminate things that are constant. For one, we know the rate constant is constant, so the K is always going to drop out of this situation. And you'll see why I picked 2 over 1. This takes a little bit of experience and insight, and it's not going to be incorrect if we did 1 over 2 or 1 over 3 or 3 over 1. It's just a little bit easier, and you'll see why. So first I'm going to pick the rate from number 2, which is right here, 2.7 times 10 to the negative 7. And I'm also going to drop the units in my equation because I can see all the units are going to be self-consistent. And that is equal to K, which we know is going to drop out. And the ammonia concentration for experiment 2 was 0.1 molar. And that's raised to some power m. And then the nitrite concentration is 0.01 molar. And that's raised to some power n. And now I'm going to divide all of this by the data from experiment number 1. So then in experiment number 1, that's 1.35 times 10 negative 7 equals K. And then now the ammonia concentration was 0.1 molar. The same as experiment number 2. And if you're paying attention to this, what you can see is there's a systematic variance, right? Where in 2 experiments, the ammonia is the same, but and then when the ammonia is the same, the nitrate varies. And then in the next set of experiments, the nitrate is the same, but the ammonia varies. So that's why for 2 reactants, we have to have a minimum of 3 experiments. For 3 reactants, we have to have a minimum of 4 experiments, okay, and so forth. And so now, with this experiment number 1 here, so this was number 1 on the bottom, my nitrate concentration is 0.0050 raised to the power n. And you can see this is why I chose to do 2 over 1, because 2.7 divided by 1.35 is equal to 2. So the rate was doubled. The K is going to be the same, so it cancels. 0.1 to the m power divided by 0.1 to the m power also cancels. And then I have 0.010 raised to the n over 0.0050 raised to the power n. And this is equivalent to just 2 raised to the power n. So my equation is 2 equals 2 to the power n. So n has to equal 1. Okay. So then now I automatically know up here for nitrite, n is equal to 1. So now let's solve for the m power. Okay. So again, I'm going to erase this. And we've done 2 over 1. And that allowed us to get that the nitrite is raised to the first power. So now I want to compare experiments where nitrite doesn't change. And that's experiments 3 and 2. You can see in 3 and 2 it doesn't change. And I'm going to do 3 over 2 so that I get a whole number. So I can do 5.4 divided by 2.7 instead of the other way around. I think it's easier to have whole numbers instead of fractions. So that's now going to be 5.40 times 10 negative 7 equals K. And then now the ammonia concentration for reaction 3 is 0.200 raised to the power m. And then we know the nitrite is 0.010, and that's raised to the power 1. I'm not going to write that because that's implied. And that's all divided by 2.70 times 10 to the negative 7. And that also equals K times now the ammonium concentration for reaction 2, which is 0.100 raised to the power m. And the nitrite concentration is still 0.010 raised to the first power. All of that cancels. The K cancels. 5.4 over 2.7 is exactly 2. And that equals 0.2 divided by 0.1 raised to the m power, which is also 2 to the m. So m equals 1. So we determined that both m and n are 1. And so when the question says, use the above data to determine the reaction orders and rate law, the rate law is rate equals K times NH4 plus times NO2 minus, both being to the first power, meaning ammonium is first order, nitrite is a first order, but this reaction is second order overall. So in other words, right, when I have, for each time I have a collision, I get a square of reaction rate. Okay, so if the reaction concentrations double, the rate goes up by a factor of 4. If the reaction goes up, if the concentrations increase by 3, the rate increases by 9. So because each of these are to the first power, 1 plus 1 equals 2. So that's what makes this a second order reaction. There's a square effect with concentration. Okay, so now I'm going to keep moving forward in this lecture, and what I'm going to do is summarize reaction orders of 0, 1, and 2. We're going to talk about all of the data, all of the observations you would get for 0, first order, and second order reactions. And then that will be the end of this lecture. Okay, so let's move forward. So, and the first thing I'm going to talk about is a first order reaction. Okay, and what I want to note is, again, when we say that this is a first order reaction, someone would have had to have done the experiment and figured out that it's a first order reaction. We can't just look at a reaction and know that it's a first order reaction. But a good example of a generic first order reaction would be A goes to products, like is written here. Okay. And so, that would maybe go A becomes B or something like that. All right. And we've already looked at the data. We know that this is K times A raised to the first power. So this is called my rate law, or often my differential rate law. And I'm not going to get into the calculus of this, but for those of you that have had calculus experience, if you want to talk about this a little more in office hours, I'd be happy to show you where this next equation comes from. But you do need to know how to use these equations. This next one is called the integrated first order rate law. And it goes as the following: natural log of the concentration of A at any time t. So that's what that means. That means this is the concentration at any time in the reaction t. So that could be 2 minutes, 3 minutes, 5 seconds, 49 years, whatever, but not 0. So that equals negative K, my rate constant, times T. So this T and this T will be related to each other. So if this is 10 seconds, this will be the concentration at 10 seconds, plus natural log of A initial. So that 0 is for T equals 0, or for the initial A concentration. And what we have here, the reason why this equation is written in this form, it is written in the form of a line, y equals negative mx plus b. Okay? So this is pretty cool. And so now, and I'm going to show you a plot of this here in a second. But now if we also think about our units of the rate constant, this is also going to be important. I want you to know units of rate constants, because the unit of a rate constant is going to change whether it's first order, second order, or 0 order. And so there's a couple different ways we can work out what the units of this have to be. I'm going to rearrange this equation algebraically, all right, and show you that if I say natural log of AT minus natural log of A0, and that still equals negative KT. And we know through log rules, I can write this in a different way. I could write this as a ratio. I could say natural log of AT over A0 equals negative KT. And then I recognize that this side of the equation is going to be unitless, okay? And if time is in seconds, then that means this rate constant has to be 1 over seconds, because a second times a 1 over second is unitless, and this side of the equation is unitless as well. So write that down here. Units for first order rate constant must be 1 over seconds. And so that very much is the same as a frequency unit, right? That's the unit of a hertz. Okay? But now if we were doing our time in minutes or years or hours, you know, it would be 1 over minutes or 1 over years. Basically, the units of a first order rate constant is 1 over time. So now I'm going to keep going with this equation right here. I've got, see, this natural log of AT over A0 equals negative KT. If I take the E of both sides, I'm going to show you something else here. All right? So if I take the E of both sides and do some algebra, then I get the following. It becomes AT equals A0 times E raised to the negative KT. So basically that's this equation right here. Take E of both sides. That's where you get E to the negative KT, and then multiply A0 over there. And so what, hopefully you recognize that this is exponential decay. So this is important to note. First order reactions are exponential decay reactions. And there's a lot of examples in nature of exponential decay reactions or even exponential growth reactions. So technically COVID-19 is exponential growth. So that means it is a first order process, right? Biological growth is exponential, so it's first order. So that's if you were thinking about the products, right? If we were thinking about B is going to have exponential growth. So that's going to look like this, okay? But, and that's for the product. But A, on the other hand, is going to have exponential decay. So that's a sign of a first order reaction, this exponential growth or exponential decay. So if I move on here, and these graphs don't really do a good job of showing you this. Here's an example of a first order reaction. Ozone reacting with light, H nu, that stands for light, so this would be a photochemical reaction. And this graph that they're showing you here, this is supposed to be an exponential decay graph, though they didn't do a very good job of showing you that. But if you were analyzing this data and you didn't know if this was a first reaction, second order, zero order, right? Here we have the, what we would do is we could take the concentrations, okay, so versus time, and what we would specifically want to do is take the natural log of concentration on the y-axis. So here you can see on this data plot at 0 seconds, we have 1 times 10 minus 4 molar ozone. Take the natural log of that and you get negative 9.210. And then so on. At different times, you're getting different concentrations and you take the natural log of those. And now if you plot those natural logs versus time and you get a straight line, then it tells you it's a first order reaction. This is yet another way of determining if something's a first order reaction. And now if you notice this equation here, this y equals mx plus b, all right, the intercept, let's circle some stuff. The intercept is going to be, right, the natural log of the initial concentration, so that's cool. And then the slope of this line equals k. So technically it's negative slope equals k. So that's really cool, right? So this actually shows us the rate constant acting as a constant. Now this will only be the case in a first order reaction. So for example, if you plot natural log of concentration versus time and it doesn't give you a straight line, it's not a first order reaction. And I'll show you an example of that momentarily. Okay. So I'm going to move on and now just speak of one last aspect of first order reactions. So we recognize first order reactions are exponential decay, such as this. Okay. When you plot natural log of concentration versus time, you get a straight line, and the slope of that straight line is the rate constant. And then the last thing that we will talk about is the half-life, and that's the time required for a reactant to reach half its original concentration. All right, and the equation from that is given as the following. So I'm not going to make you memorize equations. I'm going to give you equations, but you have to know how to use them. The half-life, as given a t1/2, it's technically equal to t1/2 natural log of 2 divided by k. The natural log of 2 is 0.693. So this is the equation for half-life. And if you think about this for a second, because the units of k are 1/seconds, when you look at this, this will be a 1/1/seconds, which just gives you seconds. All right? So this is our equation for half-life, and we're going to do plenty of examples with this momentarily. All right? So I'm going to move on now to doing second-order reactions. Okay? So in a set, and I'm going to erase all this stuff right here. All right? So now here is a good example of a second-order reaction. Maybe A plus A goes to products, where, this is first order in this A and first order in this A, giving me second order overall. I could also have that as A plus B, first order in A, first order in B. Okay. So we know that that's the same as saying 2A. So we're just going to do this example of A plus A, but we know that this could also be like A plus B, and if it's first order in this and first order in this, that would still give me a second order reaction. So then we know it's going to be rate equals K times A squared for this reaction for second order. But if it was the A plus B case, we recognize that it could be A times B, and that's still going to give me a second order reaction. So I'm only going to worry about the integrated rate law for this case right here, because it does get a little bit more complicated when we do the A plus B case. So my integrated rate law for second order goes as the following: 1/A at any time equals KT plus 1/A initial. And this equation has been rearranged to give you a line. So that's Y equals mx plus b. All right. And we could fiddle around here for a minute and figure out what our units have to be. So if I rearrange this equation and say 1/AT minus 1/A initial, and that equals KT. And if T is in seconds, and then this is in mole per liter, this side ends up being 1/molarity, which is liters over moles. All right. And now if we think about what these units have to be, there's a couple different ways I could do this. I could multiply the T over to that side. And if I did that, I would find that my K has to be liter per mole per second. Because again, if my T is in seconds, and if I say a liter per mole per second times a second, that gives me liter per mole. So write that down. Units for second order K have to be liter per mole per second, or it could be 1/molarity second. That's another way of writing it. Okay. And then also, if we look at this line, the way this works out for second order, if I now plot still time on the x-axis, but now 1/concentration, then you can see based on this, I have a positive slope. So my line will look something like that. My intercept right here will be 1/the initial concentration, right, for my intercept. And the slope will also be the rate constant. And again, it's graphed and analyzed in a way that's constant. That's a constant slope throughout the whole time, which is also very cool. Okay. And so an example of this here, if now we look at this reaction, 2 NOs makes 2 NO plus O2. And then this data, people took the time versus concentration data and plotted it. And they plotted it in two different ways. One by saying natural log of concentration versus time, and another by saying 1 over concentration versus time. And actually, let's see if I can edit this document as we go. Yes, so the fact that this did not result in a straight line tells you no dice, that it's not a first order reaction. So then the fact that now you plot 1 over concentration versus time, oops, nope, didn't want to do that. I'll just do a check mark and say, yep, that checks out. I plotted 1 over concentration versus time. That gave me a straight line. This tells me this has to be a second order reaction. Okay, great. And so now a half-life equation for second order reaction is T1/2 equals 1 over K times concentration, and that's initial concentration, all right? And so now if you think about this, if the units of K are liters over mole per second, and concentration here is mole per liter, then what that gives me is, once again, a 1 over seconds, which just equals seconds, and that makes sense because it is a half-life. And again, the unit doesn't have to be second. It could be minute, years, hours, days, whatever's appropriate for the time scale. But we do have to recognize the unit of K is liter per mole per time. So liter per mole per minute, liter per mole per year, whatever, right? As long as liter per mole per time, okay? So the very last one that I'm going to go through are zero order reactions. And surprisingly, it's very difficult to come up with an example of a zero order reaction. And what a zero order reaction means is there's no dependence on concentration versus time. The reaction just proceeds constantly. So, and typically, a good example of a zero order reaction is when something is catalyzed, and we're going to talk about what a catalyst is. But it doesn't have to be that all zero order reactions are catalyzed reactions. So, but the best example of demonstrating this zero order reaction, right, is if we said rate equals K times A to the 0 power. Anything to the 0 power is 1, so the rate just proceeds as the rate constant does. And so to make the integrated rate law out of this, this is simply just going to be time. Concentration of A at any time equals negative KT plus the concentration of A initially. And so now what that means is the K has to just have the same units as rate. And if rate is molarity per second or mole per liter per second, then K is also mole per liter per second. All right? And then if I plotted time versus just concentration, not 1 over concentration, not natural log of concentration, just concentration, then I get this constant rate here. I can see the intercept is exactly equal to the initial concentration, and its negative slope equals K. All right? And so then, of course, so this is a good example of that, right? My y equals negative mx plus b. And then my half-life equation for a zero order reaction is T1/2 equals A initial divided by 2 times K. Okay, so I'm going to summarize all these things that we just talked about. Oh, sorry about that. So here is a summary of everything. So that was a lot that I just went through. This is all of the information that I just summarized. So 0, first, second order. Here are the rate laws. Okay? Here are the integrated rate laws. The plot needed for a straight line. the slope of that straight line, the half-life of that equation, and the units of the rate constant. And so now I'm going to highlight here everything that I'm going to give you for the exam. Let's see if I'm good at highlighting here. Okay, so maybe that button, I think, here. 1 second. Well, I thought I could highlight it. Maybe. Okay, so let's do it like this. I'll just draw a box around it. And with no fill. Oh, beautiful. Here we go. Okay, so now I'm going to highlight everything that I'm going to give you for the exam. So this is what you're going to have on the exam. I'm not going to make you memorize integrated rate law equations. I'm going to give you these equations. You have to know which is which. So I'm just going to put the equations on the page, but you have to recognize that zero order is just concentration. First order is natural log of concentration, and second order is 1 over concentration. The other equations that I give you, or will give you for the exam on the exam crib sheet, will be the half-life. So I'll give you these half-life equations, but you have to know which belongs to which. And whatever is not highlighted or boxed in red on this summary sheet, I'm going to push save. There we go. Whatever is not highlighted on here, I want you to know that. I want you to have that information committed to memory. Okay, so that's it for this lecture. Let's see what we did here on the learning goals. Know how to write a general rate law and understand the components of that rate law. So that's concentration, rate constant, and reaction order. So be able to determine reaction orders and rate laws for method of initial rates. I have not released your virtual lab for kinetics yet. You are going to do a virtual lab, but that's exactly what you're going to do in that lab, is this method of initial rates. So you really want to have that down when we start to do our virtual lab. Know the units of the rate constant for 0, first, and second order. And then this learning goal here, number 6, know how to use all of these things. That's going to be a subject of another video. I'm going to have a problem solving video. And I think I'm just going to make it only problem solving. And so that will cover this one. And then look, even this learning goal right here. Know the plots needed to generate a straight line for 0, first, and second order. So we've moved a pretty good way through these learning goals. So I'm going to give you, I haven't decided, either 2 or 3 more videos to finish off this lecture. So you'll just have to wait and find out. But this will be the last lecture that I record for this week. And I'm going to generate a quiz based on just this part 1 data, set of information. All right, folks. I hope that you keep working through and making good progress. I have an office hour at 10 a.m. on Zoom, Monday through Friday. Don't hesitate to chime in. Several people have been chiming in, and it's a pretty, it works pretty well, I think, doing the office hour over Zoom. And just make sure, as soon as I release these lectures, that you're staying up with everything, that you're doing the quizzes that I post, and you're keeping up with your homeworks and stuff. All right, folks, I'll see you later.